So I spent a lot of time so far in this chapter talking about infrared spectroscopy, right? But we know there's two types of vibrational spectroscopy, and the other main type is called Raman spectroscopy. So the main difference between these is that infrared spectroscopy is an absorption technique, right? Light comes in, IR light comes in, and a molecule absorbs light, and you're looking at what light is being absorbed and what light is being not absorbed. Well, basically, you're looking at what light is being not absorbed, and you know how much light you started out with, so you can deduce how much is being absorbed, okay? With Raman spectroscopy, it's a scattering of light that you're looking at. And so, you know, all objects scatter light to varying degrees, but in the Raman effect, what happens is that some of the light, when it scatters off of an object or a molecule, it actually causes a change in the light's wavelength, okay? And so the good news is for this chapter is that we've built up all this intuition about how infrared spectroscopy works, how quantum mechanics ties into selection rules and symmetry. All of that buildup is all the same for Raman spectroscopy. And as you'll actually see, it's a lot simpler to interpret Raman spectra. So that's what the Raman effect is. All solutions, like I said, all objects scatter light to some degree. All homogeneous solutions will. Usually in chemistry, we try, you know, simple chemistry, we're trying not to do with things that are heterogeneous. So a small fraction, usually this is less than 1/100%, is scattered at lower or higher wavelengths, with the energy difference being absorbed or emitted by the scatter, okay? So you have a molecule, you put light in, and there's a chance, a low probability, but there's a chance that a little bit of that light will be absorbed. And as a result, the light that bounces out will have a less energy, so it will have a higher wavelength, right? So that's it, like a physics term for that would be inelastic scattering. Most of it's elastic, light comes in and just bounces off like a billiard ball. But there is some inelastic scattering. And the opposite can also happen where light comes in and then that molecule gets excited and actually emits light. And so emits a little bit of energy. And so the emitted light that comes out of it, that scatters off of it, has actually more energy or lower frequency or higher wavelength, right? So we call it Stokes radiation when scattered light increases its wavelength. That's most probable. That's usually what happens. And that kind of makes sense, right? That's a traditional inelastic scatter, right? Light came in, molecule, some of the light got absorbed by the molecule, and then the light came out at a higher wavelength, lower energy. So that's like a billiard ball that hit a dampened surface. And so that's kind of typically what happens, right? It's also possible, but less probable for the other case where you actually get higher energy coming out. That's called anti-Stokes radiation. And that has a lower probability associated with it. So there's different modes of Raman spectroscopy, and what we just described is called normal Raman spectroscopy. Just people call it Raman spectroscopy. Okay, this was the first type of Raman spectroscopy that was discovered. And this is, like I mentioned, a very low probability event, only less than 0.01% of incident light undergoes this Raman effect. And so as a result, this normal Raman spectroscopy has very low sensitivity. What you'll do is you'll use monochromatic light, so that means laser, right? And it'll have to be really intense light. And you'll actually spin the sample in like a test tube or something like that. And that's to limit photo damage because you don't want to blast any one portion of the sample for too long. Otherwise, you're going to probably degrade it, okay? Nobody does normal Raman spectroscopy because the sensitivity is so low, it's typically not useful. Instead, what people do is what's called resonance Raman spectroscopy. And this uses a laser with a wavelength that also causes an electronic transition. we'll get into electronic transitions at the end of the course, but basically electronic transition is actually exciting an electron, electronic transition, to another state. So far, we're just talking about atoms moving. But if you put in more energy, i.e. visible or ultraviolet light or near infrared light, we're kind of in the mid to far infrared light we've been talking about. But if you put higher energy into a molecule, then you'll have enough energy to actually excite electrons to different molecular orbitals. And that gives rise to electronic transitions. So it turns out that if you do this, and we'll talk more about why this is later in the course when we talk about some other different spectroscopies, but if you use a laser with the right wavelength that causes an electronic transition, you will really increase the probability of Raman. This kind of makes sense. The simple way to think about this is that, hey, you got the electrons into an excited state, so the whole molecule is sort of excited, and as a result, things are more willing to vibrate and move around, and that just leads to more pronounced Raman effect. I mean, that's a really sort of imprecise way of thinking about it, but it's fine, and it's how I think about it, okay, most of the time. So this is called vibronic coupling, this idea that I just described, where the electronic states being excited helps you increase the probability that you'll get normal modes being excited and therefore see an enhanced Raman signal. It required the invention of tunable lasers, so you could change the wavelength of your laser. But this is pretty much always used instead of normal Raman, just because you get so much more signal. So one concept in Raman that doesn't really frequently have an analog that's used experimentally, although in some cases it does, in infrared spectroscopy, is polarization. And so laser light is polarized. And so, we talked about polarization in IR when you have a well-oriented sample, or I mentioned that you can use this on a surface in the PM and iris experiment. But polarized Raman transitions are also observed in randomly oriented samples, not just on well-ordered samples. And there's a reason for this, and what this has to do, what we have to do to kind of talk about this is something called depolarization ratio. And so basically this ratio is the fraction of incoming light that's perpendicular and parallel polarization. So it's best to see this with sort of a depiction of how this is going to work in terms of your sample and the detector. Okay, so you're going to shoot your laser in this way. So let's say your laser is polarized light and it has this kind of polarization in the Z direction, up down here. And then what's going to happen is, you're going to get scattering. And so if you put your detector out here, right, this is your detector out here, this is your laser. Let's say scattering occurs. So scattering is going to occur. That's what the Raman effect is all based on scattering. And some of the light that comes back will have varying polarizations. It's not all going to be necessarily the same polarization that you started with. You can see if you put in a parallel polarizer that is also has polarization so that it only filters out the Z polarized light, you can detect how much light, the intensity of light that remained parallel. So that's what we call I polarized, okay, or I parallel. You can then repeat the experiment and do it with a perpendicular polarizer and get out that value, okay? The ratio between the two with the perpendicular one or the depolarized one is called the depolarization ratio, often given the signal rho. And so what you need to know for this is that if you do a resonance Raman experiment, you always have the option to perform this depolarization experiment, and it's quite easy to do. All you need is these polarization filters, which are easy to get, and then you just change the position of the polarized filter and measure the intensity difference. And so you'll very frequently see in reported Raman spectra these depolarization ratios given. The depolarization ratio for a totally symmetric mode, i.e. A1, A1G, something like that, right? Ones across the board, is going to be 0. Because something that's totally symmetric isn't going to change the symmetry of the light coming in. So whatever the polarization was, right, you're not going to get anything that's changed polarizations. Remember, these are the ones here that change polarizations, right? When you change the orientation of the filter to be perpendicular. It's the molecule symmetric. Light bounces in, bounces out the same way. It's all symmetric. For all other normal modes, when you have some asymmetry, so this could be like B1 or T2, anything other than A1 or A1G, right? Anything other than totally symmetric with ones across the board, that's going to have a depolarization ratio of about 3/4. Where that 3/4 number comes from, we don't have to worry ourselves with it. You can prove that it should be about 3/4 with some math, but that's not really important for us. Basically, we just need to know that, hey, if we get a depolarization ratio, a rho of 0, it's going to be a totally symmetric mode, A1 or A1G. Otherwise, it's going to be some value greater than 0, probably close to 0.75. And that's going to be some, other symmetry mode that isn't A1 or isn't A1G. And so that will really help us in our interpretation of Raman spectra and vibrational spectra in general, these depolarization ratios.